In this video, I'm going to discuss the renin-angiotensin-aldosterone system. This series of enzymes, hormones, and other effector tissues are responsible for regulating blood pressure, that is, increasing low blood pressure. Here, we see the kidney. We see that there is arterial blood entering the kidney and venous blood exiting the kidney. And if we zoom in at the corticomedullary boundary of the kidney, we see nephrons. For some perspective, this is the glomerulus, a capillary bed. This is receiving arterial blood via the afferent arteriole. Filtrate is formed in the glomerular or Bowman's capsule, and then the filtrate proceeds to flow through the proximal convoluted tubule, loop of Henle, distal convoluted tubule, and then finally drain out the collecting duct. I have zoomed in on some distal convoluted tubule cells, as well as some collecting duct cells. We can also see that after flowing through the first capillary bed, blood exits and flows through the peritubular capillaries and also the vasa recta. We're going to focus on this exchange of materials between the distal convoluted tubule and collecting duct with the blood. We can see here that the blood drains out and ultimately drains out of the kidney in the venous return to the heart. Anything that ends up in the collecting duct is going to ultimately drain out the ureter onto the urinary bladder. So this is a major effector tissue of the renin-angiotensin-aldosterone system. One further note, essentially the filtrate is more or less complete by the time it gets to the distal convoluted tubule and the collecting duct, and so we can monitor the filtrate contents way down here in the distal convoluted tubule and ultimately change what is coming in, what the glomerular filtration rate is going to be, and therefore what we end up releasing in the urine versus retaining within the blood. And so in reality, the distal convoluted tubule passes right by the afferent arteriole and glomerulus. So that's what this is over here. Technically, it is continuous with the loop of Henle and collecting duct, but I have just shown it over here to show that it is actually close in proximity to this system here. Anyway, first, when there is low blood pressure, that incoming blood, arterial blood in the afferent arteriole, is going to stretch mechanoreceptors lining the arterial wall. These mechanoreceptors are called juxtaglomerular cells, JG cells, also called granular cells. This reduction in stretch is going to trigger the JG cells to release renin into the blood. And that's going to be a major piece of this puzzle. It's going to trigger a larger systemic response. Other stimuli, in addition to low stretch, therefore directly indicating low blood pressure, is sympathetic nervous system can activate these JG cells via binding beta-1 adrenergic receptors. Furthermore, the macula densa cells are continually monitoring salt concentration within the filtrate. If there is low blood pressure, essentially the filtrate is going to flow through the nephron really slowly, and therefore there's going to be more time to reabsorb a lot of salt. And so if there's very little salt here, that is also indicating that there is a low blood pressure. Okay, so the macula densa cells, if they detect low salt in the filtrate, they are going to inform the juxtaglomerular cells the issue. And again, in response, the JG cells release renin into the blood. Now the blood flows out of the kidney in the venous circulation, and before returning to the heart, it is going to encounter, or on its way to the heart, it is going to encounter a liver protein called Angiotensinogen. This is a large glycoprotein, and renin, as an enzyme, is going to cleave off 10 amino acids of Angiotensinogen. Okay? And I know this circulatory pathway is not actually the pathway of circulation. I am just showing angiotensinogen in the liver because the liver synthesizes this protein. So again, renin is released in response to low blood pressure under a variety of different ways of detecting that low blood pressure. Renin encounters angiotensinogen in the blood cleaves off 10 amino acids, therefore producing the peptide angiotensin I, or Ang1. Ultimately, this blood returns to the heart via a vena cava, pumped through the right atrium, right ventricle, and out into the pulmonary circulation. While it is passing through the lungs, angiotensin I encounters an enzyme in the lungs called angiotensin converting enzyme, or ACE. ACE is going to cleave off 2 of the 10 amino acids in angiotensin I, leaving us with a peptide called angiotensin II. Now, angiotensin II is its own hormone and has receptors throughout the body. Okay. Angiotensin II flows back into the left side of the heart, which then pumps it out to the rest of circulation. The rest of the systemic systems of the body. Okay. There are receptors for angiotensin II, again, throughout the body, and so I'm going to walk through some of these now. Okay. Angiotensin II binds to receptors in the hypothalamus, specifically within a region called the subfornical organ. This is going to trigger our thirst response. Okay, so if our blood pressure is low, we can start drinking more water and therefore have more fluid in our body to increase the volume of the blood and therefore increase the blood pressure. There are also receptors within this subaoptic nucleus, suboptic nucleus, the paraventricular nucleus. Okay. Neurons from these 2 nuclei are going to be triggered to release a hormone into the blood circulation of the posterior pituitary gland. So here we can see the portal system that is to the anterior pituitary. Here is the posterior pituitary gland, and the hormone that is released from these 2 nuclei is called one of 2 things: Arginine vasopressin, AVP, or, both of these mean the same thing, antidiuretic hormone, ADH. ADH is going to directly tell us what this hormone does in the kidney. Okay, so this hormone is released and ultimately is going to act on the kidney. We'll get to that in a moment. Angiotensin II also binds to receptors on our blood vessel walls. Specifically, this is going to trigger vasoconstriction. So we used to have these big, wide blood vessels. They are going to constrict. When the blood vessel's diameter is lower, the pressure is going to increase. Now, this is not a long-term solution. Okay, this is just a temporary fix. Again, the problem is low blood pressure, so we are going to vasoconstrict in order to increase the blood pressure temporarily. Finally, angiotensin II is going to bind to receptors on the specifically zona glomerulosa of the adrenal cortex. Okay, remember, the adrenal cortex sits right on top of the kidney, but we have zoomed in a little bit here. So the outermost layer of the adrenal cortex is going to be stimulated by angiotensin II. This system uses an IP3 DAG second messenger system, and ultimately this is going to turn on enzymes that ultimately lead to the synthesis of aldosterone from cholesterol. Okay, so aldosterone is released into the blood. ADH is released into the blood. Both are going to have effects down here on the kidney. Okay. Finally, angiotensin I, so before it was converted into angiotensin II, angiotensin I also has the ability to bind to receptors within the adrenal medulla and trigger them to release norepinephrine into the blood. And so a lot of different hormones are being released in response to renin's action on angiotensinogen and ACE's action on angiotensin I. Okay. So again, collectively, ADH, aldosterone, and to an extent norepinephrine, released into the blood and ultimately end up in the kidney. Okay. And once again, I know that this is not an accurate circulatory pathway, but I just want to show you that all of these things end up in the arterial blood and into the kidney. Okay, so what exactly happens? Let's start with aldosterone. Aldosterone is going to bind to mineralocorticoid receptors within the distal convoluted tubule cells, as well as over here in the collecting duct cells. Now, mineralocorticoid receptors have about an equal affinity for both aldosterone as well as cortisol. So any of these steroid hormones have the ability to trigger the response I'm about to talk about in the distal convoluted tubule cells. So we know that there's a lot more cortisol in the blood than there is aldosterone, and so cortisol does have the ability to trigger this effect. The reason why we see aldosterone producing most of the effect is because there's likely more of this deactivating enzyme, 11-beta-HSD2, that deactivates cortisol in these cells, so that only aldosterone is triggering this effect. Right? So this works as long as there's not an overabundance of cortisol. If there is an overabundance of cortisol, then there's only so much 11-beta-HSD2 available, and so some cortisol is going to trigger this effect as well. And as we see, there's going to be a subsequent increase in blood pressure. Okay, so that's one of the secondary effects of cortisol on blood pressure. Okay, so back here, aldosterone binds the mineralocorticoid receptor, and it's going to do a couple different things. And again, this is happening in both of these types of cells, so let's zoom in over here. The aldosterone mineralocorticoid receptor binding is going to trigger the expression of genes within the nucleus. First of all, it's going to trigger the synthesis of ENaCs, epithelial sodium channels. And so we're going to insert these epithelial sodium channels into the adluminal side of the cell. And so what that's going to do is it's going to allow sodium to flow from the urine, or the soon-to-be urine, it's still filtrate, into these cells. Okay, similarly up here. Okay, these are passive transport channels, and therefore we need to first generate a concentration gradient. Okay, so here we can see that there are sodium-potassium pumps and sodium-proton pumps, both of which pump sodium into the blood. So essentially we are retaining a lot of sodium, we are reabsorbing a lot of sodium here, and we're leaving a low sodium environment into the cell. And so sodium is going to flow from high concentration over here in the filtrate, down its concentration gradient through the ENaC into the cell, and finally be pumped into the blood. Okay, so at the same time, we are reabsorbing a lot of sodium from the urine, ultimately into the blood. We are exchanging potassium and hydrogen. And so on the adluminal side of the cell over here, we see hydrogen channels, right? So proton channels, as well as potassium channels. And so there's generally this exchange, right? So sodium is retained, but the compromise is that potassium and hydrogen are released as well. Okay, and so this is just one other way that we maintain this high sodium and low potassium concentration in our extracellular fluid. Okay, so again, long story short, aldosterone, which is triggered by the release of renin by the juxtaglomerular cells, ultimately leads to the production of angiotensin II, which releases aldosterone, which reabsorbs a lot of sodium, so it increases sodium in the blood. Okay. The other thing that angiotensin II did was trigger the release of ADH, antidiuretic hormone. Antidiuretic hormone is going to act on cells of of the collecting duct as well. Here we see ADH, also called AVP, binding to its receptor. It uses a cyclic AMP second messenger system to transcribe and ultimately activate aquaporin 2 channels. Okay, so just a reminder, aquaporins allow for the passive flow of water with the osmotic gradient. So essentially water follows salt. We just put salt back into the blood, so water is going to be inclined essentially to follow the salt back into the blood. And so on this side of the cell, there are always aquaporins. And so aquaporin type 3, aquaporin type 4 are always on this side of the cell. But we can selectively put aquaporins on this side of the membrane. Okay? If we have a ton of water in our body, we can just urinate away a lot of water. But if our blood pressure is low, we want to insert more of these channels in the membrane and therefore provide an opportunity for water to flow down its concentration gradient and back into the blood. And so instead of having a lot of urine volume, right, so a lot of water in your urine, now you have all that water back into your blood. More blood volume equals higher blood pressure. Okay, so in this way, aldosterone is creating a concentration gradient, and water is following that gradient. Okay, so we are reabsorbing both sodium and water back into the body. Both of these collectively are going to increase the blood pressure, not just for a few minutes, but for the relatively longer term. Okay. Once again, this has been the renin angiotensin aldosterone system. Low blood pressure is detected directly by the JG cells, indirectly by the macula densis cells, and also we get a sympathetic nervous system stimulus of these JG cells. Ultimately, renin is released, cleaves angiotensinogen. The resulting angiotensin I is converted into angiotensin II by ACE in the lungs. Angiotensin II stimulates thirst, stimulates the release of ADH, vasoconstriction, and the release of aldosterone. ADH and aldosterone act on the kidney. Specifically, aldosterone, via a mineralocorticoid receptor, is going to increase sodium reabsorption in the distal convoluted tubule and collecting duct, and AVP, arginine vasopressin / antidiuretic hormone, is going to trigger the insertion and activation of more aquaporin 2 channels in the membrane of the collecting duct, which ultimately retains water. The problem was low blood pressure. We are fixing the low blood pressure by reabsorbing a lot of water. Thank you so much for watching this video about the renin angiotensin aldosterone system.